Okay, we continue. Now we will do the SSI. SSI. Okay, it's a very short one. Microcontroller, I will show TI. I know the most. So I will show TI and I know TI C2000, something like this. This one. Oh, 2000. Okay. C2000. Yes, we can take the more advanced. Real-time microcontroller. Okay. Take this one. And copy it here. Okay. Take it here. Reject. Okay, and then now we need to see what we will say. What the hell, where? Maybe in future we would say 2000 megahertz. Keyboard 2000 megahertz. Bandwidth with 64 bit flash memory. Flash. 5.12 kilobyte flash each CPU. Kilobyte per CPU. Number of pin 169. Converter. Yes. How many bit? Precision. Two point. So this one. Okay, so it's 133 bit. This one 33. Okay. 62 bit. Okay. Okay. get have and sitting with more and more. Okay. Richard via do not read that form. What operating system Arduino? Yeah. System. Okay. Okay. Real-time operating system. Symbol. Real-time operating OS. Micro OS and Lean on real-time operation system. Real-time operating system, something like this. Real-time operating OS và nó đây còn vậy. Right. Okay, we put like that. I think we have variety of aligners. Oh, right. Okay. A lot. We put some Ubuntu may cái đây là Ubuntu free BSD, something like that. Ubuntu free BSD. Made and many more. Many other. Okay, done. Wait. open source and nó open source. I think all of them are open source. Open source. Okay. Okay. Then send the order. Yes, 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 yes. Okay, okay, okay. Oh, true. I should one. Okay. It's okay. Good. 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 What the heck? No. Put something not good here. Play. Do a correct. Play. Does it? Play. Do it correctly. Do it correctly. 0, 0. 0, 0, 0, 0. Okay. Okay. One more. This one good. Good job. Okay. Okay, okay, okay. What is it? Wait, here, what is it? Okay. OSMC. Oh, it have. Okay. Good. Good to know. Okay. Okay, okay, okay. Okay, okay, okay. Okay. So we continue to the last week is land the view of networking and basic networking hardware. Okay. We try the intrusion of the internet. We try the meaning of a network protocol in plan, manage, and generation through IoT. Okay. Mobile work. Ready for the thing. Okay. Security and the thing. We are repeatedly history. We repeating history. Something to read with the OS. Okay. So that is okay. Okay, 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 okay. Then we stay.
So networking is clearly an important part of Internet of Things. Internet is right there in the name. So in Module 4, we'll talk about networking in general. We'll talk about networks, network protocols. We'll focus on the Internet because that's the network to which we will most likely be connecting. Also, we'll talk more specifically about mobile ad hoc networks. Mobile ad hoc networks, or MANETs, are small networks of mobile devices, which IoT devices commonly are. And they're ad hoc, meaning they're changing all the time. Things move in them, things move out of them, and that's inevitable when you're using mobile devices. The configuration of the network can change very dynamically. So we'll talk about MANETs and how there are different protocols used for MANETs and how you design and implement an Internet of Things component with networking in mind.
Networking basic.
In this lecture, we'll talk a little bit about networking. Networking is a central feature of Internet of Things. We'll talk about why it's needed, how it's helpful. Also, we'll start talking about general structure of networks, sort of the broad categories of networks. Why is networking needed? Well, it enhances devices. It makes things better, let's say. So it enhances features by giving you access to computational complexity outside of the local device. So if the Internet of Things device is a camera or a phone or a car or whatever it is, the fact that it's connected on a larger network means that from that smaller device, you can access much more powerful servers, much more powerful, much bigger databases. You can access all that through whatever the device is. And having access to all this computational power and all this data can be leveraged to enhance a lot of devices and improve their features. So for instance, cars, say cars, Internet of Things device, they can communicate with each other on a network to improve traffic flow. So wouldn't that be great if cars were all talking on a network and they could plan their own routes and consider the fact that other cars were planning their own routes? They could collaborate together to make the flow fast, right? Which, by the way, is possible and probably will happen in a decade or so. But it takes a while to get those things worked out. But that's probably going to happen. There's no reason why that can't happen, and that would be very useful. So it's an example where you're enhancing the feature of a car by using the networking. So they can now talk to each other. They can talk to a centralized database and get mapping information and things like this. Online gameplay, we all know about that, or I do. So there are a lot of games. In fact, there's a large segment of games where you can't. There isn't much to play by yourself. You have to play online, right? Call of Duty, for example, or Destiny, or whatever. Those games, you play them online, and it opens up a whole new world to you, literally, right? Many new worlds. You can connect to different people and do all sorts of extra things that you couldn't do locally on one machine. Accessing media libraries, Netflix, for instance, right? Or Amazon Instant Play, or whatever library you're using. You can only access those. So sure, maybe you're using a TV as your Internet of Things device, but it alone doesn't have the library of all movies ever created, right? You have to connect through the network to Netflix database or whoever it is. So networking is useful. It's very useful. It enhances abilities of any particular device. Now, the communication between an Internet of Things device and the main network is usually, most commonly, follows a client-server model that we're showing here. So the client would be the Internet of Things device, right? And that's a smaller machine, relatively less powerful machine, connected to some server, and you see that in the middle of the server. It is guarding and protecting some resource, giving access, let's say, to a resource. So you see the resource over there on the side. The resource can be any kind of resource. Maybe it's a web server, and the data for the web pages is in that resource or something like that. And then the server gives access to that resource. So the client, which might be the Internet of Things device, that thing is communicating, making requests of the server to get whatever the appropriate information is. The server then manages the resource, so it handles the request, gets whatever it is that is needed from the resource, and sends it back in the form of a response to the client, which would be your Internet of Things device, and maybe you see the web page, or you have whatever data you were looking for, or you get the movie that you wanted to look for, something like that. So this sort of client-server model is very common. The client is generally less powerful. That is, it's a smaller machine, literally less power, it's slower. Where the server can be a very large cloud-based server, very powerful, plugged directly into the wall, has lots of power, cooling fans, whatever it has. So and the resource can be whatever you want, mega disk drives and some machines, whatever you want. So this is typically the model that you see Internet of Things devices communicating with the network through. So we're going to talk about three really broad classes of networks right now. First, LAN, local area network, stands for. And a local area network is just a relatively small network. Usually spans building a campus. A campus might have one local area network, a floor of your building. You've had experience with local area networks, I'm sure. Now, typically, the way you access these networks is either through the wall, socket, an Ethernet jack in the wall. See one right here. Also, Wi-Fi routers. I see one in here too, right? So we're familiar with those. Local area network is commonly for building or something relatively small. Okay. Now, on the other side of that, there is a wide area network. The other extreme. Wide area network. The best example of that is the internet itself. That's an extremely wide area network. And a wide area network is just a lot more complex than a local area network. There's a hierarchy of machines that are communicating together. So it's really a wide area network is really a different class of network than a local area network. Has different protocols involved. And internet is basically the wide area network that we'll be talking about. Now, in addition to this, we have mobile ad hoc networks, MANETs. These are actually important to Internet of Things components because mobile ad hoc networks they're composed of largely mobile devices. That's the term mobile. And a lot of Internet of Things devices are mobile. And it's an ad hoc network because it reconfigures itself constantly. So that is maybe an Internet of Things device, a cell phone, let's say, comes into range of the network, then it joins the network, but you continue walking and you walk another block and you're outside the network, right? So the network is reconfiguring every few seconds. Maybe something's walking into the network, something's moving out of the network. It's very dynamic. So that's what a MANET is. And a lot of Internet of Things devices are part of a network like that, of a MANET. And you need different protocols for that. You have to assume low battery, assume things are mobile, so power is a constraint, right? Because you're usually battery driven if you're mobile. So they have a different class of algorithms for MANETs as well. Thank you. The internet is a wide area network, the wide area network, and that's generally what we want to communicate with eventually. So we're going to talk about the general structure of a wide area network. These pictures are pretty high level, but they give you the general picture of what a wide area network like the internet would be, how it's composed, and what the different components are inside there. So a wide area network like the internet is a network. It's a combination of local area networks. So if you think about the internet, it's very ad hoc, right? There's no regularity. Meaning anyone can, like right now, if I wanted to, I could build a network right here in this building, and it would be added to the internet. I could give it a name, and it would be part of the internet. And so the internet isn't one of these networks that's controlled and well structured, right? Unlike the local area networks that you see at your place of work or at a school, where you have some IT department, IT group, and they constrain how the thing is put in there. They say, look, every time a machine comes in here, you got to register it in this way, and we only approve this and that. And they put the equipment into the building for you and all that. So it's very structured. But generally, wide area, the internet specifically, is pretty unstructured, right? And there is some minimal structure, there has to be, but it's fairly unstructured. So at a low level, at the leaf level, right, local area network level, there can be any number of different local area network types involved in the internet, right? Just depending on what people want locally. So you start off with local area networks. So we got a local area network, and you got several hosts, host 1, 2, 3, and these hosts are just computational devices that talk on the network. So basically computers or IoT devices, and they're all communicating with a component. Now in this picture we got a switch. It could be a hub or a switch. A hub is a network component that it has several input ports. We're assuming wired right now. This can also be all done wirelessly, but let's talk wired for a minute. It's got several input ports, input-output ports. Like in this case, the switch has 3 ports, right? So you can have a hub there that has 3, and anytime data is a packet is sent on one of the ports, it is reflected, copied to the other ports. So if host 1 sends a message to anybody, that same message is spit out to host 2 and 3. So both of them get the message. That's all that a hub does. A switch is more intelligent. A switch says, look, it looks at the packet header to see where it's going. So if host 1 sends a message to the switch, and it looks at the destination of that message is host 3, then the switch there is smart enough to know that that message should only be sent to host 3, not to host 2. So the switch is more intelligent about where it sends messages to, where a host is more dumb. But you got a host or switch somewhere in there that transmits data between the different input ports and output ports. So generally LANs look like this. Now you can have larger LANs, which involve multiple protocols. So you see on the left you got a LAN, on the right you got a LAN. You can combine them with a bridge. The bridge can communicate different LAN protocols. So maybe you've got these LANs, and one department in the university decides they want to use this particular protocol. Another department uses another particular protocol, but they want their machines to communicate, so they put a bridge in between, and the bridge basically talks both protocols and can do conversions between the two. So you can group together these LANs into larger LAN components, let's call them. So something, it's not a single LAN anymore. You can have multiple protocols that are glued together by this bridge. Now, a wide area network is a set of these LANs all put together with routers. So if you look at this network, this is by the way a simplified internet, but you got a bunch of LANs, and they're all communicating to routers. And then the routers can communicate with each other to pass data. So one LAN can communicate with a completely different LAN through these routers. So you notice every message is sent from one machine to another has many hops, what are called hops. It has to go through several different machines before it reaches its destination. So if you want to go from one LAN to another, you might leave this LAN, go to this router, then go to another router, then finally back to the destination LAN, and then to the host. So there's a sequence of hops. It's called a route, actually, of hops that you have to go through to reach your destination. And so these routers, they're organized. This is very simple. It's only 3, but in reality, there's a vast hierarchy of these routers, and they are all intelligent. They have intelligent protocols to determine where they should send the packet next to reach its destination most quickly and avoid flow. You don't have one router that receives too much data. Maybe all the messages are running through one router. You'd like to spread out that data across the entire network so that the one router doesn't get bogged down. So there are lots of protocols along those lines, and the internet involves protocols like that to sort of level out the traffic. Thank you. So we've been talking about networking. We've been talking about the different components that you find inside networks. So I thought that since I had some of these components lying around the lab, I'd show you some of these, let you get a look at what they look like in the flesh. So first is a hub. This is an Ethernet hub. These are hard to find. They don't make many of these anymore, but this is a hub. This is a 4-port hub. It's got 4 Ethernet jacks. You can plug 4 things in. And it's very simple what a hub does. It receives a packet on one port, and it just copies that out onto the other 3 ports. So it's just a repeater in that sense. It's very dumb. And it's wasteful in terms of bandwidth, right? Because if you're sending a message from this port to this port, it doesn't need to appear on these 2 ports, but it does anyway. So there's extra traffic with a hub. It's dumb and wasteful in terms of bandwidth. That's why you don't see them too much anymore. So that's a hub. Next up is a switch. This is a switch. It's a bigger switch than that hub. This switch has 16 ports instead of 4 that you saw on that hub, but the number of ports is variable. But this is smarter. So what it does is it receives packets on, say it receives a packet on this port. It doesn't just send out blindly to every other port. Instead, it learns over time which ports are connected to which IP addresses. So it can look at the packet header and determine which port it expects to see the destination on, and only send that message on that port. So if it receives something on this port, and it looks at the header and says, oh, that device is on port 10, then it'll only send it out on this port, and that saves bandwidth. So that's a switch. This is a router. It's actually a wireless router, Wi-Fi router. And it's got some lights on the front. You've seen these. You probably have one at home, or you've seen them on the wall in your office building, something like that. This is a router. On the back, it's got an antenna. It's a wireless router. On the back, again, it's got Ethernet ports. same as the switch and the hub. One thing to notice about these 3 devices is that they are very similar. I mean, their interfaces are similar. They're just a bunch of Ethernet jacks, right, and some lights. Ethernet jacks and some lights. This one, Ethernet jacks and some lights. Now, this also has a wireless antenna because it's a wireless device, but generally these look basically the same. They only differ in how they function, how they respond to messages, and where they reflect messages to.
Okay. Yes, we see this one.
So this lecture, we'll talk a little bit about the internet and structure, and we'll get into internet protocols in general. We'll talk about what a network protocol is. We have to know a little bit about these. We don't want to go into detail in protocols, but you have to know they exist because the hardware that we buy when we make our IoT device, the hardware that we buy, we'll buy it matching a particular protocol. So we'll pick the protocol and pick the hardware to match that. So we need to know at least the existence of protocols and what they are. So internet structure is ad hoc. That is, it's very irregular, right? People can join the network, leave the network. I can open up a laptop in this room right now, and suddenly it will be part of the internet, right? People can send messages to it. And then if I shut it off, it is now temporarily no longer part of the network. So the internet is very dynamic. Somebody can build up a new network right now, plug it into the wall, and bam, there's a new addition to the internet. And that happens all the time. So it has an unpredictable structure, but it still has to work. Actually, it's pretty amazing that it works as well as it does, given the fact that it's so crazy. So it can be changed by anyone anytime. So you have to be able to send messages between this wide variety of network types, right? So you've got these LANs that are maybe use different protocols, routers that are speaking different protocols, destination LAN that speaks a different protocol. And so you've got this, you got to be able to consistently send messages regardless of everything else. So that means if I set up a host in my office, I set up a network in my office, that thing has got to be able to talk to some LAN on the other side of the world without knowing anything about the protocol of that LAN, right? And without only minimal about it, right? I don't know what type of protocol they're going to use on that LAN. All I know is I want to send a message to a machine in that LAN, right? So you have very little structure, but you still have to have some level of uniformity so that everybody can talk. So how is it possible to send bits meaning messages, across these networks, hop to hop, through these different networks with different different protocols, essentially? So we'll talk about these protocols. Let's define them. What protocols are basically a set of rules, specifically rules of communication. We're talking about network, for network protocols, a set of rules of communication. And there are a lot of rules, but generally it's a set of rules, hopefully a minimal set of rules, which as long as everybody adheres to those rules, everybody can communicate, okay? And you want to make these rules minimal so that they're not a burden on the local area network. So you want to give people who are building their local area networks as much freedom as you can as to how they design their network. But there have to be some protocol rules that they adhere to, some minimal rules, which will allow them to communicate with all the other local area networks through the internet. So the internet has protocols associated with it, which if you want to talk on the internet, your networks have to support these protocols. Now, just to give you some intuition about what a protocol is, it's basically something that you add. It usually involves adding data to a message, okay? A regular type of data to a message. So if you ever watch old movies or cop movies, something like that, and they're on the radio, right? And they say something over, right? Over. They say over at the end of their message, right? And as soon as they say over, somebody else can start talking, right? And then when they're done, they just say over and out, right? So this is a protocol. Because what it says is every time you send a message, I don't care what the content is, I don't care what the words are, just make sure that at the end of that message you say the word over, right? And no matter what the content of the entire conversation was, just make sure that at the end of that conversation you say over and out. As long as you follow those rules, everybody can talk. Because the goal of those protocols is the radio protocols with humans talking on radio is so that two people aren't talking over each other, right? You want to make sure that one person's talking at a time. So whoever's talking can keep talking until they say the word over. When they say that, the other person knows, oh, now it's my turn, and they talk until they say over. So over is like passing the baton to the other person to talk. And as long as you adhere to that, to those simple rules, it doesn't matter what you say, what the content is, you can talk with somebody else. Now there are limits to that, right? Because there's no rule about how long you can talk before you say over. So you can just talk all day and then finally say over, and then you would be a bottleneck to the network, and that would be a problem. So internet actually has rules to handle that, right? There are time limits and things like this. But you get the idea. A protocol is basically extra data that you add, is represented by extra data you add to the message, like the word over or the word over and out, right? Or there are all kinds of rules and extra data you put in there that are used to enable communication. So we call that protocol, that set of rules that enables communication, which minimally constrains the message. It adds a little bit of data to the message typically. That's what a protocol is, and TCP/IP is the most common set of protocols for internet. In fact, specifically, IP stands for Internet Protocol. And if you're using the internet, if you want your machines to talk on the internet, they have to use Internet Protocol. They have to adhere to the rules of IP. Now, TCP/IP, TCP is another protocol, and that protocol is it also is used in conjunction with the internet. So if you're using internet, you're either using TCP or UDP, right? And you're using IP. So I said TCP/IP. It could also be UDP/IP, Universal Datagram Packet, if I recall, protocol. Sorry, and IP. You put those together, and that's internet. So you can do anything else you want. You can add all kinds of other data into the message. As long as you adhere to those protocols, you can talk on the internet, and your machines can communicate with other machines on the internet. Thank you.
Protocol.
So we'll talk a little bit about protocols, network protocols, internet protocols specifically, and what their responsibilities are. We won't go into great depth, but we want to give you a flavor of what's contained inside these protocols and what they define. So what does a protocol do? An internet protocol, it does a lot. An internet protocol, meaning IP or TCP or UDP, they do several things. One basic thing is provide a naming scheme. Actually, that's a very important thing. So IP, you probably heard of an IP address. That comes from the internet protocol, and it's a unique address that every network component has. Every component on the internet has to have an IP address. And so each host and router gets assigned at least one of these internet addresses. Now, when you say at least one, basically it should be one to every network adapter. But a particular machine can have many network adapters. By network adapter, I mean hardware interfaces to the network. So if you look at a laptop, you'll often have a Wi-Fi adapter, but you'll also have a wired adapter and a wired Ethernet jack. You might not, depends on your laptop, but you might have an Ethernet jack where you can plug into the wall, right? So you might have two network adapters there, two Ethernet network adapters. So you might get two IP addresses, one for each. Usually you focus on one, but it's possible to have more. So internet protocol, one very important thing it does is give this naming scheme, this unique naming scheme. Every machine on the internet has to have a different name. And now there are problems with this, right? Because IP addresses are not that long. IP addresses are four single bytes. So you've seen them referred to as like 128.254.27.33, okay? And there are four numbers separated by dots. So it's four numbers, and each number can range from 0 to 255. So there aren't that many addresses compared to how many network components there are these days. It's because of IoT, there's so many things on the network, you need so many addresses. So there are a lot of challenges in dealing with that. We won't really cover those right now. But the idea is everything on the network has to have a unique IP address. Also, these protocols provide a delivery mechanism. So what we mean by that is that whenever you send a message from one machine to another machine, you've got to go through a sequence of machines. Okay, you got to define a packet, a certain amount, a chunk of data, and it's got to be sent from machine to machine to machine because these machines are not directly wired together, not within radio range directly. There has to be a route taken, so it has to hop from one machine to the next. So these protocols define methods of doing routing, right? Of how you send a message through a sequence of machines to get to the destination you want to go to. That's one important role. Another thing is it defines the header, right? The header and the payload. So by header. So if you look at any packet, you can usually break it up to header and payload, maybe footer too, but let's just talk about header. So payload is the actual data that you want to send. The header is the information that is a sort of metadata. It's about the packet, but it's not the actual payload of the packet, not the important part of the packet. It's not the data you want to send, but it has information about the packet. Now, generally, the header information comes from the network protocols. So the data in the network protocol that the network protocol uses, it gets put into the header, typically. So we'll look at that a little bit here. So yeah, actually I brought this up last lecture. Citizen band radio, you say over at the end of talking, and Roger means data received, and so on, right? So that would be called footer, right? So you say a message, and then at the end of your message, you say over. And that word over is actually added to the end of the message. So the payload is the text. So say I say something like, hello, my name is Ian Harris, over. Hello, my name is Ian Harris, that's the actual payload. And then the over is overhead, right? We call that footer because it's at the end. But text, if you put something you add to the beginning, you call header. And header and footer, same thing, beginning and end, but it's the same thing. Excess overhead data that's required to help you adhere to the protocol, but it's not the actual data that you want to send. So these rules enable efficient communication. These rules, these header and footer rules, the data that you put in them, you need that so that at the receiving end, you know, like for instance with CB, you know, oh, I heard the word over, that means I can talk now, right? So in order to establish efficient communication, you need that information is contained in the header and footer. And for instance, with routing in the internet, some of that information inside the header will be important for routing, right? Things like this. So all the different functions that these protocols handle, they use information inside the header typically to do that. There are many different tasks that are performed by protocols, by network protocols. A lot of different tasks, and we can't go into the details of all those, but some of those are routing, figuring out a route, a sequence of machines to send a packet through to get to its destination. Flow control, right? So making sure that you don't have a bottleneck, that all of your traffic isn't going through one router, that you spread it out over different routers so that you can get good traffic flow. Arbitration. Arbitration means when you have some kind of a network segment where only one packet can travel at a time, then two packets want to travel. So say two machines want to send messages on this one piece of network segment at the same time, then somehow you have to arbitrate. You have to figure out which one gets to go first, right? So there are rules for all these things, and all these rules are encoded inside the network protocol. So the protocols define those rules. What do you do when two machines want to talk at the same wire at the same time, right? The set of rules that's called network protocol. And when you want to send a message from A to B, how do you figure out what the next node is that you want to send your message to, right? That's defined by the protocols and so on. So these protocols are very complicated in general. And because they're so complicated, what people have done is they've divided the protocols into layers. So OSI, Open Systems Interconnect model, OSI model, it presents what's called a protocol stack, classification protocol. So it takes all the things that these network protocols do and divides them up. So routing is one layer, flow control is another layer, arbitration maybe is another layer, right? It just separates them. Now, all of these layers have to be taken care of, but the separation is generally good for coding, frankly, because writing one piece of code that handles all those complex tasks at once, it would be one nasty piece of code. So it makes a lot of sense to cut that code up to separate the responsibilities across different layers, and then write different pieces of code for each layer, and then let the different layers of code work together. So that's what the OSI model does. It presents proposes a set of layers. Now the internet uses a similar set of layers, maybe a more compressed version of that, but definitely the idea of taking all these complicated tasks and dividing them amongst different layers of protocols is a good thing to reduce the complexity and make the coding more manageable. So each layer has its own responsibilities, and each layer uses different data. So different data usually in the header, right? So for instance, if you're looking at routing, there's a layer that's doing routing, you're going to need to use routing information in the header and actually place routing information in the header. Where if on the other hand you're working on flow control, right, and flow control is maybe a different layer, then flow control doesn't necessarily need to know the routing information, not the details of it, but it might need to know the capacity at a node, how many messages can a particular node take at one time. So that would be different information that also might be present in the header or something like that. So each, or not in the header, but each layer uses different types of information to do its job. Thank you.
Okay.
This lecture, we'll talk about what protocol stack is, really define that term. We will go into a little bit of detail, a little bit of information about how a protocol stack is defined. Now, remember though that in practice, certainly in this specialization in practice, you're not going to be writing a protocol stack, making a protocol stack, but you can use a protocol stack. So we want to know what this term is because it gets thrown around, right? If you want to make a new embedded system, you say, well, I need to be networked, internet. Which protocol stack am I going to use, right? Which implementation of the protocol stack will I use? You need to know what that term means because it gets used a lot when you're actually coding things. You should know basically what it means. So not all the details that I'm talking about will be important in the long run, but you should see it all once because it'll give you better context about what you're using. So OSI layer concept. So the idea about taking these protocols and making a stack, different layers of protocol, is that you've got these multiple layers, different tasks, different networking tasks you have to handle. These tasks are associated with different layers of the protocol stack, and each layer is implemented usually in software. Actually, some of the lower layers are implemented in hardware. So some are in hardware, some are in software. That doesn't the difference doesn't matter too much to us right now. Certainly the top layers are in software. But the idea is that a message, say you want to send a message. Okay? So you make this message, like we got a picture of here, this message M. M is our message. And that's maybe just the payload. Okay? That is what the data that we want to send. So then that is basically an input to a layer. Let's talk about the first layer. Layer R, let's say is the first layer, the top layer. So that goes into it, into the code. So that code takes the message, it makes some kind of a decision, whatever decisions are made at that layer, and then it puts the results of that decision into the header of the message, producing a new message, M prime down there, which is now bigger. It has whatever was inside M, and it has additional header on the outside of that, right? So at every level that happens. So the first level, so for instance here, let's say this level is performing routing. Okay? So the goal of this level is to take a message and figure out a sequence of machines that it will hop through to get to its destination. So at this level, it takes the message, it finds the route, it says, okay, you need to go through machines A, B, C, and D, right? That sequence. So it could take that sequence, that whole sequence of nodes, put that into the header of the message, and then output this new message M prime, which is the same old message, but now with this routing information contained inside the header. So that's the general idea that at every level, at every layer, the code or the hardware, whatever it is that's implementing the protocol, will make some decisions like routing information, arbitration information, flow control information, and then the results of that it'll put into the header, or some of the results it'll put directly into the header, and you'll get a new message out, which is bigger than the original one, right? Which now has this new header data. This is on the sending side. So this is the idea, and you have a stack of these layers. So that's what they mean by protocol stack. You have layer after layer, and they call that stack. Now, encapsulation is used to mean that the protocols they're separated from one another in some sense. So each protocol layer is separated. So all these different tasks that need to be performed, say routing, right? That is mapped to a particular layer. That's performed by the protocol information stack at this layer. And other layers do not have to deal with it. So it is encapsulated, it's separating the different layers. And the whole point of that is to make it simpler to understand and also to write code. Right? So as a programmer, if you're dealing with a layer that deals with routing, then that's all you have to think about. You don't have to think about flow control because flow control is dealt with at another layer. So that's what encapsulation generally means. And a protocol stack is the implementation of all different layers put together. So at transmission, when you want to send a message, basically the messages start at the top layer and then they go down, right? So you put the message into the top layer protocol, it makes its decisions, adds to the header, passes it to the next layer, which makes some decisions, adds to the header and continues until you get to the bottom layer. Now the bottom layer is called the physical layer, and at that layer it actually takes the data and puts it onto an electrical mechanism, a transmission mechanism, some kind of medium. So that means one of two things: either wires, so physical layer, it encodes the data onto wires, physical wires, or it encodes it onto wireless broadcasts, radio broadcasts. So one of the two. It's always the bottom layer is this physical layer, which actually transmits the signal either by wire or through the air through radio. Now, at the receiving end, the message comes in, remember it's sent physically, right? So it's on wires, it's a bunch of electrical signals on wires, or it's sent through the radio. So at this end, the messages go up through the same protocol stack. So that means when it's received at the physical layer, right? Because it's physical signals, either wired or wireless. They come in and they have to get basically recoded back to the original data, right? So now at the receiving end, these messages are going through the protocol stack up, from bottom up. And so the opposite of what happened on transmission happens here. So at every layer, the message gets received, the appropriate header information is read and used, and then the new message is produced is actually smaller than the first message, minus that header information. Right? And then goes up to the next layer, which takes the header information at that layer, uses that, and then produces a new message, which is smaller. And so by the end, at the top, all you have is the actual payload, and all the header information has been stripped off. So that's what happens at the receiving end. The reverse of what happens at the transmission side. Thank you.